What is an FRF? What is a frequency response function maybe of this pan? What is a FRF at all? Well, it is the base for many high-end performance analysis in acoustics. You need FRFs for modal analysis. You need them to do a transfer path analysis. You need them for dynamic stiffness analysis of bodies. Well, there is a high-end maths behind. You need complex vibration equation. You need differential equation. There is E by the power of complex I multiplied with circular frequency by time. The good news is nowadays you don't need to understand all the mathematic background because all the math stuff is done in modern software automatically. Just drag, drop your measurement, and there's even artificial intelligence inside that checks out your measurement and optimizes the parameter to get your optimized results, okay? But I recommend you should understand what is a frequency response function, what data information is contained therein, okay? And then you are completely safe and can work with that. So I will teach you that information just in a few minutes, right here. Let's start simple. Well, this is a pan which has two endings, one below and one on top ending where I hold the stick. And if I move down the top end, you will see the lower end will also move exactly the same amount. And even if I make it very, very fast, the distance between these 2 points will always be the same. Of course, because it is a rigid body. Now we do exactly the same with a system that can swing. Now the lower point can move independently of my top point. Let's see what's happening now, all right? So I'm moving 2 centimeters down, and this also. I move 2 centimeters up, and it will also just follow my system as long as I'm moving very, very slowly, okay? So the duration of this movement divided by this movement will always be 1, okay? If I'm moving a little bit faster, I mean the changing of being on top or below, if you think of a circle here, you might see that the lower part, the mass, have an extra weight. It goes a little bit further than my hand. If I rising the frequency of the circle, it's getting even more clear. Now the mass moves more than I put in on top. It's getting wider and smaller because I make a higher frequency impulse always in the timer, see? And it's getting even worse and worse and worse. The higher the frequency, I even have to draw down here now my impulse here, my movement, because it's completely weird. Now, the reaction amplitude is much bigger than my input amplitude, okay? Because I raised the frequency of this incoming circle, okay? And there is a certain frequency, if I just stimulate the system in that frequency, it gets a lot of energy just by doing almost nothing. But the frequency is right, he goes completely out of bounds. I'd like to break, okay? This is an important frequency. We call it in German Eigenfrequency. You can call it natural frequency in English, okay? Sometimes I call it Eigenfrequency, because Eigen is just the German word for own. But there's also another very important effect. On low frequency, they all move at the same time, high position, down position, high position, down position. If I'm going to the natural frequency, there will be a time shift. Looking at the top points, it's top, 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 top. So there is a time shift. If you're thinking about circles, yeah, you can say one time around 360 degree, but now these circles have a phase difference. You can call it in degree, okay? So this degree will be in this natural frequency about 90 grade, okay? And that is the reason why it's always get more energy every time the cycle continues. It's like you're pushing a child on a swing. You don't push with the velocity in the point when it's down, when it's already had the velocity. No, to bring the energy in, you get the energy when at the highest point when standing. Now I'm pushing the velocity in, and it's getting even more velocity. Every time this is pushing the velocity when it's not half velocity gives it even more. Every time more energy in. So having this phase difference of 90 degree pushes the energy in. But what happens if I stimulate this oscillating system with this frequency above the natural frequency? Let's try. I make it like this. And you see now the phase is exactly against. And when I'm moving down, he's moving up, down, up, exactly the different motion it's now in that system, okay? So the phase difference is 180 degrees. And as you can see, the amplitude relation, I move more than he's doing, okay? Because I'm above the natural frequency. If I'm moving very, very fast, it seems like he doesn't move at all. So we see the amplitude relation between the end and the beginning drops almost to zero, and the phase relation stays constant, minus 180 degrees. So actually he is working against the stimulation. And this is the crazy thing about oscillating system. It does not depend how big my movement is. It's only interesting how the frequency is, okay? Depending on the frequency, it's a response with a different amplitude ratio and with a different phase ratio. So we should write this down in the graph. One graph shows you, depending on the frequency, what is the amplitude, and the other graph gives you what is, depending on the frequency, the phase relation to the incoming signal. So this complex function describes now the response of this swinging system from there to there as a function of the frequency input. And that's why this is called the frequency response function. That's simple. Okay, this is a very basic frequency response function because a very simple system. But what will happen to our swinging system if it has to move through oil? So we add some damping, or if we make it more complex. Right now there's only 1 degree of freedom. That's why we only have 1 natural frequency. But if we add another spring and another mass, 2 degrees of freedom, what will happen then? We do this in the next video, okay? 1 steps, and finally you get to the answer, what is the frequency response function of the pan. So stay tuned. Just click.